NASA's Space Launch System, abbreviated as SLS, is the most powerful rocket the agency has ever built. Designed to carry astronauts beyond Earth orbit for the first time since Apollo, it forms the backbone of the Artemis missions that aim to return humans to the Moon and eventually push toward Mars. But what makes the SLS different from rockets that came before it? And what are the engineering challenges behind getting such a massive vehicle off the ground? Let's break it down. NASA aims to lay the foundation for future missions to Mars by learning how to live, work, and engineer in deep space environments. At the heart of this vision is the Space Launch System, NASA's next-generation heavy-lift launch vehicle. Unlike launchers designed for low Earth orbit or satellite deployments, the SLS is built specifically to propel large payloads beyond Earth orbit, where gravitational and propulsion demands are significantly higher. It's the only rocket currently certified to carry both astronauts and heavy cargo to deep space in a single launch. Each Artemis mission will rely on the SLS to launch the Orion spacecraft, NASA's crew vehicle for deep space missions. Orion is designed to sustain astronauts for weeks, navigate long-duration lunar orbits, and interface with the Lunar Gateway, a small space station that will orbit the Moon. Depending on mission design, Orion may dock with Gateway or perform a direct-to-lunar orbit rendezvous for surface missions like Artemis 3. What sets the SLS apart from commercial alternatives like SpaceX's Falcon 9 or Falcon Heavy is its mission profile and design philosophy. The SLS is NASA-owned, government-operated, and built from the ground up to support deep space crewed exploration, not commercial satellite delivery or cargo resupply. In its current Block 1 configuration, the SLS can carry more than 95 metric tons to low Earth orbit and about 26 metric tons to the Moon via translunar injection. This makes it the most powerful operational rocket in the world. Future versions, such as Block 1B and Block 2, will feature upgraded upper stages and more powerful boosters, eventually enabling up to 130 metric tons to orbit. This kind of raw lifting capacity isn't just about size, it's about mission flexibility. With the SLS, NASA can launch entire lunar missions, crew, supplies, habitats, and surface equipment in fewer launches, reducing risk and complexity. It's a critical enabler of high-mass, high-energy mission profiles that would otherwise require complex on-orbit assembly using smaller commercial rockets. In short, the SLS is not just a launch system. It's the foundation of NASA's deep space architecture and the engine driving humanity's return to the Moon. Let's take a closer look at how the SLS is engineered from bottom to top. Starting at the base and extending up along the core of the rocket are two massive solid rocket boosters. These 5-segment boosters are an evolution of those used on the Space Shuttle, but with an additional segment added for even greater thrust. Each booster produces over 3.6 million pounds of thrust, and together they generate more than 75% of the total force required during the first 2 minutes of flight. As they ignite, flame and smoke billow outward, propelling the vehicle off the pad and into the sky. Next, we move to the core stage, the structural and propulsive heart of the SLS. It's a towering 64.6-meter-long tank made up of 2 cryogenic chambers, one for liquid hydrogen, the other for liquid oxygen, which feed the rocket's 4RS-25 engines. These engines are high-efficiency, liquid-fueled engines originally developed for the Space Shuttle. Unlike their shuttle configuration where they were reusable, the RS-25s on the SLS are optimized for a one-time deep space launch. Each engine can throttle and adjust thrust, providing controlled and sustained propulsion after the boosters separate. Once the core stage completes its burn, it separates, and the interim cryogenic propulsion stage, or ICPS, takes over. This upper stage is equipped with a single RL-10 engine, which performs 2 key functions. It places the Orion spacecraft into orbit and then, after a coast phase, executes the translunar injection, the maneuver that slings Orion out of Earth orbit and toward the Moon. The RL-10 is known for its precision and reliability, and its design has evolved from decades of upper stage applications. Sitting at the top of the rocket is the Orion spacecraft, NASA's next-generation crew vehicle built for multi-week deep space missions. Orion features an advanced heat shield, a service module for power and life support, and modern navigation systems for docking and rendezvous. During ascent, it's protected by the Launch Abort System, or LAS, a solid motor power tower that can pull the capsule away from the rocket in a split second if something goes wrong. From its boosters to its upper stage, every component of the SLS is designed with one goal: to deliver astronauts safely and efficiently beyond Earth orbit. It's a vertically integrated system, each piece engineered to work in precise coordination with the next. Together, these elements make the SLS not just powerful, but adaptable, capable of launching cargo, crew, and habitats to support the Artemis program and future deep space missions. However, before the SLS could ever lift off the pad, it had to prove itself through one of the most rigorous test campaigns in NASA's history. From individual components to full system integration, each piece of the rocket was put through environmental, structural, and performance trials, ensuring that when the time came, everything would work as expected. The centerpiece of this testing phase was the Green Run test, a comprehensive, full-duration firing of the SLS core stage conducted at NASA's Stennis Space Center. During this test, all 4 RS-25 engines were fired simultaneously for over 8 minutes, simulating an entire launch profile from ignition to main engine cutoff. Engineers monitored engine performance, structural vibrations, fuel consumption, and flight software in real time, validating the integrated stage under actual launch-like conditions. Meanwhile, components like the ICPS and the Orion capsule were tested for pressure, vibration, and extreme thermal conditions to verify their resilience in deep space. As the individual components passed their tests, they were shipped to Kennedy Space Center, where NASA's ground crews assembled the full launch stack inside the Vehicle Assembly Building, the VAB. Here, integration testing ensured that all subsystems, propulsion, avionics, communications, and structural interfaces functioned together as one. This all led up to the historic Artemis 1 mission, the first full launch of the SLS. On November 16, 2022, the rocket ignited and lifted off from Launch Complex 39B, marking the beginning of a 25-and-a-half-day uncrewed mission around the moon. The Orion spacecraft traveled more than 2.2 million kilometers, entering a distant retrograde orbit around the moon before safely returning to Earth. Artemis 1 validated every major component of the launch stack, from launch to orbital insertion to deep space navigation to re-entry and splashdown. The data gathered from this mission is now being used to prepare for Artemis 2, which will carry humans aboard Orion for the first time. With this milestone complete, the SLS isn't just a concept anymore. It's a proven vehicle, ready to support the next era of crewed deep space exploration. As Artemis 2 and Artemis 3 prepare to fly in the coming years, the SLS will be tasked with safely carrying astronauts farther than any rocket before. It's not just a launch vehicle, it's a bridge to the moon, to Mars, and to the future of space exploration. Thanks for watching. If you enjoyed this breakdown, be sure to subscribe for more deep dives into the technology shaping our future in space. Let us know in the comments, what space engineering topic should we cover next?